In this lesson, we're going to talk about an introduction to systems of linear equations, and then we're going to go through solving them graphically and numerically. So what is a system of equations? Well, when we have multiple equations with several unknowns are just variables, the equations may be solved simultaneously as a system. A system of linear equations can be solved graphically, numerically, algebraically by substitution or elimination. Now, I emphasize that they have to be linear equations because if we have nonlinear equations, something like x squared in there, we're not going to be able to do all of these methods. So when I'm solving a system of equations, what type of solutions can I expect? Well, we can expect that we have one unique solution, meaning that there's one ordered pair that's going to solve both of those equations. That implies that we have a consistent, independent system. So that means that there is one intersection between the two lines. I could also have infinitely many solutions, meaning that every single ordered pair is a solution to the system. So that's why in type number 1, I say that it's one unique solution. That means that there's only one possible combination of x and y that will solve my system. Whereas in number 2, it's still solutions. You have a solution. It's just that there's an infinite number of them. So we have a consistent system because there is a solution, but it's dependent because every single answer is a solution. The last type is that there is no solution, meaning that there's no intersection between these two lines. There's no x and y values that will solve both equations at the same time. So that implies that we have an inconsistent system. So let's take a look at a few examples. So my first example here, I have y equals 4x plus 3 and y equals negative x plus 2. So what's nice about this is that we're already set equal to y, because when we solve graphically and numerically, we need to be in that y equals mx plus b form so that we can graph our equations. So we're going to do so using the graphing calculator. We start by going to the y equals key. In y1, I'm going to type in the 4x plus 3, and in the y2, I'm going to type in negative x minus 2. Be sure to type in a negative sign in front of the x and not a minus sign. If you get an error, that's likely where it is. After that, I'm just going to look at a standard 10 by 10 graph, so that's zoom up at the top and then the number 6 for standard. Again, that gives me that standard 10 by 10. I see that we have an intersection, so in order to find that intersection, I'm going to do second and then the trace key, and I want option number 5. We're going to try to scroll as close to that intersection as we can. Then we hit enter for the first equation, enter for the second equation, and then enter as a guess. All you have to do is follow the prompts on the calculator. And we see that there's an intersection at negative 1, negative 1. The other way that we can solve this is numerically by looking at the table. So I'm going to go to second and then the graph key, because we see right above it says the word table. And we see our table, and we're looking for where the y values are the same. Wherever the y values are the same is where the intersection is occurring. And we see the y values are the same at x equals negative 1. So once again, I have my intersection at negative 1, negative 1. So just to summarize, in my graph, I saw a physical intersection here. On my table, I saw that the y values are equal here. So my solution to this system is the ordered pair negative 1, negative 1. Okay, let's try this again. So we have negative 5x plus y is equal to negative 3, and 3x minus 8y is equal to 24. The first thing that I have to do is I have to solve both of these equations for y so that I can enter them into the graphing calculator. So I'm going to show the work right here. So I have negative 5x plus y is equal to negative 3. I'm going to add the 5x to both sides. I'm left with y equals 5x minus 3. So that's the new rewritten version of my top equation. We're going to do the same process to rewrite the bottom equation. I have 3x minus 8y is equal to 24. I'm going to subtract that 3x from both sides. I'm left with negative 8y is equal to negative 3x plus 24. divide everything by -8 so that y is isolated. Y is equal to 3/8 x minus 3. That's now my new bottom equation. So these are the two equations that I'm going to enter into my calculator. So once again, I'm going to go into y equals. I'm going to put these into my calculator into y1 and y2. Be sure for the 3/8 that you do put parentheses around that value because there is no fraction key in the graphing calculator unless you have a newer version. Again, I'm going to do zoom 6 for that standard 10 by 10 graph, and I'm going to find the intersection that I see. So second trace, option number 5 again. We found the intersection graphically and numerically, so my solution is 0, -3. Okay, in this next problem, we have x plus y equals 7 and y equals -x plus 7. So I'm going to solve that top equation and enter it into my calculator. So I have y is equal to 7 minus x into y1, and y equals -x plus 7 into y2. Graphing that, we see that there is one line. So this is an example of having infinitely many solutions because it's one line on top of itself. Every single point is an intersection, so every single point is a solution to the system. And we could see that looking at the table as well. When we look at the table, we notice that every single y value matches because they're the exact same line. They're just written a little bit differently. And in our last example here, I have 2x minus 4, and I have x is equal to y over 2 plus 3. So again, I'm going to solve that bottom equation for y. I do so by multiplying by 2, and then it's easy to just subtract over that 6. So I'm going to enter y equals 2x minus 4 and y equals 2x minus 6 into y1 and y2. When I graph this, I see that I have two lines that are parallel to each other. And we know that they're parallel because they have the same slope. Both of those lines have a slope of 2. Well, when we have parallel lines, they're increasing or decreasing at the exact same rate. So it is impossible for them to actually intersect with each other. If we look at our table, we notice how the y values have a difference of 2, just like the first equation has a -4 and the second equation has a -6. There's a difference of 2 there in the y-intercepts. So this system actually has no solution. So just to reiterate what we talked about at the beginning, when we have a system of equations that are linear, we can solve them graphically and numerically, and also algebraically, which will be done in a different video. Regardless of how we solve them, we can expect 3 different types of solutions. One unique solution, that's an ordered pair. Infinitely many solutions, meaning that it's the same equation on top of itself. Or no solution, meaning that we have parallel lines that will never intersect.